Why am I so fascinated by the bee's honeycomb? For me, honeycomb is fine art. Now, the best art shifts our consciousness in subtle ways. It makes us pose questions. It drives us to feel, to wonder. It lingers in our mind long after we have moved on to the next thing in our lives. This is what the bee's honeycomb does to me. It has done this to humans for millennia, made us ask questions, find the answers, and then use those answers to create materials and structures of our own. And even after all this time, all the investigations we have carried out, the bee's honeycomb still offers mysteries and wonder to those that look close enough. The first thing that strikes you when you look at a bee's honeycomb is the cells that span it on either side. They are near perfect hexagons and have been the subject of study for centuries. However, it was only recently that it was mathematically proven that the regular hexagon is the most efficient allocation of material when it comes to dividing a space into cells. This has influenced the design of engineered honeycomb panels that have found their way into aircraft and rocket bodies, into packaging, and into crash impact energy absorbers. But there is more to the honeycomb than just its hexagonal cell. A closer inspection reveals that some of its secrets lie at a finer scale. Consider the walls of each honeycomb cell. The walls have a variable thickness, with the thickest end occurring at the very top. If you cut through these walls and look at the cross-section, they have the appearance of a matchstick tip. Now, why do bees add this extra bit of material at the top of the walls? It has been speculated that this makes the walls much more resilient against damage and also helps them retain honey better and prevent it from dripping out. Another such observation visible only on closer inspection is that the corners of the hexagonal cells are not sharp. In fact, they have very clear fillets or curvature at the corners. Why? This has been shown to minimize the amount of stress in the corners and also maximize the stiffness of the honeycomb, thereby making it less prone to deformation and failure under its own weight. Bees make honeycomb with wax, but something remarkable happens after the first year. The larvae that grow in the honeycomb cells spin silk cocoons around themselves, and that silk is not disposed, but instead embedded into the walls to give it additional strength. The honeycomb thus becomes what we in engineering call a composite. It now consists of honeycomb wax, but also silk fibers. Due to this additional strengthening mechanism, the cell walls can be thinner and still resist all the loads that the structure is exposed to. And in fact, that is exactly what we observe. The second and third year honeycomb walls tend to be thinner than the virgin one created without silk reinforcement in year one. This list of observations of the honeycomb structural detail is not a complete list, but I have to stop somewhere. There are many more interesting observations about the honeycomb. The fact that the cell sizes change in response to whether it is intended for a worker, a drone, or a queen bee, and how the cell sizes transition between these different types. The fact that it consists of two arrays of cells laid back to back instead of just a single array. The planes that occur at the intersection of these two arrays and their very specific angles of construction relative to each other. For some of these observations, we have answers. For others, we can only speculate at best. So, don't underestimate the humble bee. Biomimicry has incredible possibilities. From kingfishers inspiring train design to antimicrobial film mimicking shark skin, and cephalopods in forming camouflage. We have a lot to learn from what is around us. And for me at least, we should start with bees. The natural world has generated billions of design iterations that can lead us in all the right directions. This was ASU. Thanks for watching.